What is quantum entanglement? Quantum entanglement is a captivating phenomenon within the realm of quantum mechanics that has perplexed physicists for decades. At its core, this phenomenon describes the unbreakable connection between quantum particles, regardless of the spatial distance between them. As researchers delve deeper into understanding the intricacies of entanglement, they uncover the peculiar behavior that defies classical physics. In this video, we will explore the fundamental concepts of quantum entanglement, delve into its enthralling implications, and discuss its potential applications in various scientific and technological domains. Historical development. Born out of the theoretical framework of quantum mechanics in the early 20th century, the concept of quantum entanglement emerged as a result of Albert Einstein, Boris Podolsky, and Nathan Rosen's famous EPR paradox. This thought experiment challenged the prevailing understanding of quantum mechanics and highlighted the notion that particles could be inextricably linked. Subsequently, physicist John Bell devised a mathematical inequality, Bell's theorem, that could test whether entangled particles followed the principles of classical physics or quantum mechanics. The nature of quantum entanglement. Quantum entanglement is inherently rooted in the superposition principle, which states that quantum particles can exist in multiple states simultaneously. When two or more particles become entangled, their states become intertwined, leading to the possibility of instantaneously influencing each other's measurement outcomes, regardless of spatial separation. This phenomenon is known as non-locality, a distinctive trait of quantum entanglement that challenges our conventional understanding of causality. Einstein's famed spooky action at a distance. Einstein himself famously referred to quantum entanglement as spooky action at a distance due to the seemingly instantaneous nature of entangled particles' correlation across vast distances. This phrase reflects his skepticism toward the accepted interpretation of quantum mechanics, as it appears to violate the principle of locality, a fundamental concept in classical physics. Quantum entanglement and quantum computing. Quantum entanglement serves as a cornerstone in quantum computing, a rapidly advancing field with profound implications for various industries. Utilizing entangled particles, quantum computers can leverage the phenomena of superposition and entanglement to perform highly complex computations exponentially faster than classical computers. However, harnessing these quantum properties poses significant technological challenges that researchers are actively working to overcome. Entanglement and fundamental physics. Quantum entanglement has also played a pivotal role in unveiling the fundamental aspects of the universe. Experimental tests of Bell's theorem have consistently shown that quantum entanglement is not an artifact of hidden variables, supporting the probabilistic nature of quantum mechanics and challenging determinism. This realization has opened up new avenues for exploring the very fabric of reality and has inspired profound philosophical discussions. Applications of quantum entanglement. Beyond quantum computing and fundamental physics, quantum entanglement holds great potential for revolutionizing various scientific and technological domains. Quantum communication aims to leverage entangled particles to achieve secure and unbreakable encryption, known as quantum key distribution. Additionally, entanglement-based sensors offer heightened sensitivity in measuring parameters such as time, gravity, and magnetic fields, surpassing the capabilities of their classical counterparts. Entanglement in quantum biology. Remarkably, quantum entanglement has also been explored in the realm of biology, providing insights into the quantum processes that underlie biological functions. Researchers speculate that entanglement might play a role in photosynthesis, avian navigation, and even the sense of smell. These investigations raise exciting possibilities in understanding the relationship between quantum phenomena and complex biological systems. Challenges and future directions. While the study of quantum entanglement has led to astonishing breakthroughs, numerous challenges remain to be overcome. The delicate nature of entangled states makes their preservation challenging in real-world scenarios, rendering practical implementations difficult. researchers continue to explore methods to prolong entanglement and mitigate the impact of environmental noise, paving the way for advancements in quantum technologies. Conclusion. Quantum entanglement represents one of the most fascinating aspects of modern physics, challenging our understanding of the fundamental nature of reality. Through its utilization in quantum computing, communication, and biology, entanglement promises groundbreaking advancements that will reshape science and technology. As researchers deepen their comprehension of this phenomenon, the allure of quantum entanglement continues to capture the imagination of scientists and graduate students alike, inviting further exploration of the mysterious world of quantum mechanics.